Hello everyone, welcome to Understanding Physics, in which I will try to guide you through understanding physics. So today on General Physics 2, we want to talk about reflection as well as refraction, one of the key ideas within talking about optics. So before we get started, please consider subscribing as well as liking the video, and also please check the notes in the description for the notes within this entire discussion. So let's just straight away discuss about reflection straight away. So the way that I would define what reflection is that this is pretty much elastic collision. And not only that, what do we remember from last time is that P equals to U over C. So that means that if we have this object, and then if we have this guy to have a certain momentum, it should later reflect with a certain angle. So now we'll just assume that the energy is conserved. That means that this energy should equal to this energy, or pretty much the PC was to equal to the PC again. So this is in general anyways. But we should also think about the conservation of momentum, especially in the y direction, since there's no force that is making it going in the x direction. So we could just use our formulas to actually define what is the resulting angle when we collide this light within a certain angle of θ1. So if we try to figure out what's this x component, it will be sine θ1. This will equal to the p of the sine θ2. And then from the relation above, we know that this initial and the final one should be the same momentum. So we could cross them out. So what we observe is that this θ1 should equal to θ2. And this is literally the definition of a reflection. So this angle here on the left here is something which we will call as the angle of incidence, while on the right hand side it will be the angle of reflection. So there are two different types of reflection. One of them is called specular, the other one is diffuse reflection. So specular is if you have a very smooth surface and then you let light hit it, it will later reflect the same parallel lights. So this is the one that creates mirrors. So mirrors are specular reflectors because you could see the original image not really distorted. But for a diffuse reflection, it has jagged lines or jagged surface. So what will happen is that these light will later reflect at different angles, something like this. So the light, when you later combine them all together, it will be all jumbled up. So this is why if you have an object hitting another object in which it has high reflection, it doesn't truly mean that it will later reflect to you the same object, but instead it could be a mix of these colors, or pretty much what we denote as diffusive reflection. So this is what separates object being able to reflect image and reflecting colors. So what I want to discuss here is that you could have something called partial reflection, in which not all of the light is reflected within the surface. So if you have a object and then you hit it with a light, the energy will later turns out to be split into multiple different types of energy, or the waves. So there will be reflection, the one we have already discussed, which is elastic collision. There's also the inelastic version, which is called scattering. And you could also absorb the energy and turn it into some other work. And the last one is transmitted, in which the light could actually pass through. So there's reflection, this one is reflection, this is scattered, transmitted, and the rest is absorbed. So within this discussion, we won't fully discuss about scattering as well as absorption. So we'll only focus on reflection as well as transmission, since they both are only related with the geometry of the object. So let's talk about refraction now. So refraction is the idea in which if you have an object hitting a surface, its speed will later change. So if you have a light hitting this object, the speed is going to be different. So we have v, we have c. So the question is, what's the relation between these velocities? So we could actually do this by by actually doing just by doing the Maxwell's equation. So maybe the divergence of the E and the B won't really make anything useful, but the curl will actually make things interesting. So this is the negative partial B vector over partial T, and the negative partial vector cross B vector is going to be mu 0 epsilon 0 partial E vector over partial T. And for dielectrics, what we know is that this electric field is not exactly this value, but instead it is also multiplied by the kappa. So this is the one that we observe from the outside, and this is what is actually happening, in which this is the actual electric field. So these two values are different. But when we are dealing with vacuum, the kappa is 1. So if we also do the same type of figuring out the curl of the curl, what we'll obtain is that the speed of light within this material is going to be 1 over the square root of mu 0 epsilon 0 v. No, sorry, kappa. So what this concludes to is that this is c over the square root of kappa. So now I want to wrap this entire thing up. Let's say the c over the speed of light within this material is going to be the square root of kappa, in which we'll call this as n, or the index of refraction. Now this index of refraction is a value that is dependent on omega. And it turns out this kappa is also dependent on omega. So that means that if we figure out what's this kappa within dc, we couldn't fully determine what's the index of refraction based on that value, even though it is pretty similar. So if you go for long wavelengths, it will still make sense, but if we go for short wavelengths, in the end it will later not make any sense. So let's do a certain example in which we will just have this material, and then we shine light, and then there will be some that will be reflected, so it will have the same angle. And then there are some which is going to be transmitted. So the question is, what is this transmitted light? So let's try to solve this. We got this momentum of the reflected, and the momentum of the transmitted. So the momentum of the incident, multiply this by the theta I, and this is also theta I, and in this direction this will be the theta t. So this momentum of the incident light, multiply that by the sine theta I, would equal to the momentum of the r sine theta I plus the momentum within the transmitted direction, sine of the theta transmitted. So we could convert everything into the energy. We would get the u over c sine theta I equals to the u over c, multiply this by, so this is technically ur sine theta I plus ut over c sine theta t. So we could cross out of the c. And then we could just collect u and ur together. So remember what we obtained from the previous discussion a little bit is that u, the incident light, must be equal to the reflected plus the transmitted, the conservation of energy. So we could actually obtain that the u minus ur equals to ut. So this means that ut sine theta I must be equal to the ut sine theta t. Sorry, my bad. So this is not exactly c, but instead this is velocities. So this is the velocity of the incident, this is velocity of the reflected, this is the velocity of the transmitted. Now, let's say this material has this Ni and this Nt. So if we multiply everything by c, we could actually get this to be the N incident and the N transmitted. So it's still fine. So we will have something like this, and then we could just cross out the UTs. So what we will get is that this N1 sine theta 1 must be equal to N2 sine theta 2. So this is what we call as the Snell's law, in which it relates about whenever a light hit a particular surface, what will be the transmitted light as well as its entire thing. So it's pretty much the conservation of momentum. So there is this specific idea in which you could actually get the light not to really reflect any light. from a particular surface. And the idea is that if you actually take a polarized light and then hitting it towards the surface, it could later not really reflect anything, but instead everything being transmitted. And how is this the idea? So we could think of it like this. If we have this light hitting this object, we could have this object being polarized within a certain direction, depending on your dipole moment of this material. And within this propagating dipole moment, it could only create a electric field tangential to the, in the same direction as the propagation of this dipole moment, which is normal to the entire thing. So if we have this plus minus, we apply an electric field, it will later transmit this electric field tangential to this entire compound. So if we have this guy to be shined with light, or this AC electric field, the alternating electric field, we could have it oscillating something like this, such that this will later be 0, and this will be literally perpendicular to this reflected light. Now, what we could obtain from here is that we could get this specific angle. So let's solve for this. If we have n1 sine theta 1 should equal to n2 sine theta 2, right? And we also have a relation. This is theta 1, this is theta 2, and this is 90 degree. Therefore, 180 degree, or pi, should equal to pi over 2 plus theta 1 plus theta 2. So what relation do we get? Theta 2 equals to pi over 2 minus theta 1. And this is exactly n2 cosine theta 2. So we could actually simplify this entire thing into the tangent of, this is theta 1. So we could simplify this to be the tangent of theta 1 equals to n2 over n1. Or this theta 1 is going to be something which we call as theta p, or the polarizing angle, or Brewster's angle. So this is in which the angle of the reflected light is going to cause certain effects such that there is no reflection. So we could have this other specific angle in which we could actually get a certain object to be fully reflected, as long as we get it within a certain parameter. So let's say we have something like this. We have an n1 as well as n2, and then we shine light within this object. We want to have reflection but no transmission. So how do you do this? Well, it seems hard if you think about it in terms of the Snell's law, but it turns out that it's pretty easy. Since if we actually draw this line, what's the max in which we would have transmission? And this idea is the most fundamental part when we're dealing with this problem of total internal reflection. So the maximum at which this guy can actually become a transmitted light is a value below 90 degrees. So this is our boundary. So let's just put this into our Snell's law straight away. n1 and 2, let's just put this as n1, this is n2. So n1 sine theta 1, so this will be theta 1, must equal to n2 sine theta 2, or 90 degrees, which is 1. So this particular angle is what we call as the critical angle of n2 over n1. So this is the idea when we're dealing with optical fibers. So the idea is that you would have a object in which you could actually send information just by actually putting it inside this fiber. And so if we know what this n1 as well as this n2, what you could do is that you could just let it oscillate in between as long as you keep it at a certain angle. So if it goes above, there will be leakage of this information. But if you don't have any leakage, that means that you would have a light speed information exchange based. So this is pretty useful since, light could be superpositioned by one and another, but not only that. So that means that you could actually send one light in one direction and one light in the other direction within the same optical fiber. this is the very interesting part of optical fibers or optical connections, is that you could actually transmit data as well as receive data at the same time. Finally, I want to talk about dispersion. So dispersion in itself is a property which is very related to the refraction. So the idea is that, remember, your index of refraction is not really proportional, but is a function of your frequency. So this means that you could get certain effects, such as if you actually put this within a prism. Let's say you send in white light, a white laser. What this prism will do is that there is changes within this index of refraction, so that some of the light will bend much more than others, and then when it leaves the prism, it will later also have certain amount of refraction. And this is what happens when you try to separate light into its different colors. So this is the idea of spectroscopy, in which if you send your signal in the form of the electromagnetic wave, you could split it out into multiple different wavelengths for you to analyze for, let's say, its energy or its momentum. But anyways, this is much more related into the quantum mechanics if we are dealing with the frequency related to its energy. But for now, I will just say that you could actually separate it between each of the colors. So this is also the idea of how rainbows work. So rainbows are pretty much a sphere of another different kind of fluid, in which if you have light hitting this object, it will later have some form of refraction, in which it builds up into a rainbow. So that's all for today's video. So today we talk mostly about geometrical optics, as well as its foundational basics within optics. So thank you very much for watching, and make sure to like and subscribe, as well as sharing it to your friends who really needs to understand physics in a much more deeper understanding. So thank you very much for watching, and I will see you on the next video.